In section 6.3, they're introducing the concept of vectors. Vectors have a magnitude and a direction. Their location does not matter, which means sometimes we pick them up and move them to a more convenient location. That will make it easier for our calculations. Okay, a directed line segment can be used to represent a vector. Okay, this picture here is vector V. The initial point is P. The terminal point is Q. Okay, and now the thing about this, even though this looks like a ray, it is not a ray. It has a fixed size or magnitude. It is only this long. The arrow is indicating the direction it's pointing. It does not indicate that it goes forever because it does not go forever. It has a very specific size. Okay, for notation, I could use V to represent the vector because they told me it's a vector V. I could also call it vector PQ, and the symbol I would use is this. It just has that half an arrow, because if it had the full arrow, it would be a ray. Okay, some other notation that you would want to know, the magnitude of vector PQ. It can be denoted by this. Or because we also called this vector V, I could also denote it using this. And magnitude is the size of the vector, or in this case, it's the length of the vector. Because remember, it does not go forever. It's exactly the distance from P to Q. Okay, the next thing is a vector in standard position has its initial point at 0, 0. This allows the vector to be expressed using only its terminal point, V1, V2, with those pointy brackets. This is called the component form. So what this is saying is I have this random vector over here. I can pick it up and move it so that its initial point is at the origin. So let me just draw the origin here. Okay, same vector, same size, same everything, but I picked it up and moved it. Okay, now I can name this in what they call component form using only the terminal point. So I can represent this as V1, V2. In component form, we use those pointy brackets at the end. And the V1, V2 happens to match the terminal point because the initial point is 0, 0 at the origin. That's why standard position is so convenient, because those two always match. Okay, now the component form as a vector is the format you're going to want to use the most because it's the easiest to work with. Okay, so if they give you the terminal and initial point of a vector and you want to convert it to the component form, you just have to find the distance between the x's, so q1 minus p1, and the distance between the y's, q2 minus p2. Just make sure that you always do the terminal minus the initial. Otherwise, you have it going in the opposite direction, and remember, the direction matters. Okay, for the magnitude formula, this looks like the distance formula. This is the distance formula. Although if it's in component form like this, then it just looks like this, which is very reminiscent of finding r in chapter 4, where it was x squared plus y squared, and then you square root it because it's the same concept. And then a couple vocabulary words. If the magnitude of v is 1, it's called a unit vector. If the magnitude of v is 0, then it's called a zero vector. Okay, this first example is just to kind of give you a visual representation of all these terminology they just taught you. Because it tells me that vector u has an initial point of 0, 3. It has a terminal point of 5, 6. 1, 2, 3, 4, 5, 6. Okay, that is the end of it. I put the arrow to show the direction because it makes a difference which one's terminal versus initial, because it would be pointing the opposite direction and if it was the opposite initial and terminal points. Okay, let me now draw vector w. So vector w has initial point 3, negative 5, and terminal point 1, 2, 3, 4, 5, 6. Oh, I went off the graph. Negative 2, so around here. Okay, and remember, initial to terminal. Okay, and that is vector v. Vector w. Okay, I'm going to find the component form for u and w. Okay, let's start with u. Okay, component form, I use those pointy brackets. For the x component, I do terminal minus the initial, and you don't have to show your work on these, but these are notes, so we're going to do it that way. And then the terminal minus the initial in the y direction, which means the component form is 5, 3. Okay, now I'm going to do the same for w. Okay, pointy bracket in the x direction, terminal minus initial. In the y direction, terminal minus initial, so plus 5, which goes to 5, 3. Okay, now I'm going to redraw vector u in standard form. Standard form is the component form, using the component form with the initial side at 0, 0. Okay, so for vector u, initial sides 0, 0. In the x direction, I go 5, 1, 2, 3. In the y direction, I go 3, 1, 2, 3. And this is the new terminal side. And if you look at vector u, this is the exact same as vector u. It just got moved into standard position, but it's the exact same size, it's the exact same direction. Okay, two vectors are equivalent if they have the exact same component form. So because u and w have the same component form, they're both 5, 3, vector u and vector w are equivalent. And how I would prove it is I would show that they have equivalent component forms. Okay, for the next few examples, we're just going to play with a little bit with component form and finding the magnitude. And then that'll be it for today. Okay, so for example 2, it says find the component form and the magnitude of the vector v that has initial points 5, -2 and terminal point -1, 3. I'm going to do the component form first. Because from component form, it's easier to find the magnitude. Okay, so this is vector v. In component form, I use the pointy brackets. So in the x direction, terminal minus initial. And then the y direction, terminal minus initial. So in component form, it's -6, 5. Again, that just indicates that it has its initial side at 0, 0. Okay, I'm going to sketch it just so you can see what it would look like. You don't have to sketch it. Okay, this is saying initial side, initial point at 0, 0, -6, 5 means the terminal side's about at -6, 5. So it would look something like that. It didn't ask. I'm just showing you because I know you want to know. Okay, now I want to find the magnitude of this vector. Remember, I denote magnitude using the double bars. Okay, and magnitude, if it's in component form, I can just square each component and then square root the result. Okay, the magnitude of v is the square root of 61, and that's telling me that the distance, the exact distance of this directed line segment is exactly the square root of 61. Now for example 3, let's look at it. Okay, they want me to find a vector so that the magnitude of the vector is 40, and they want it to be in the direction of u, and they give me u in component form. U is -4, -3. Okay, I'm going to sketch u. You don't have to sketch u. I'm just trying to get you guys to relate to the vector. Okay, the u looks something like this. So they want me to find another vector v, so that's going in this direction, but the length of it is going to be 40 instead of whatever the length u currently is. So what I want to do, I like the direction, I want to figure out what length u currently is, and I'll figure out how to make it longer. Okay, so the length of u is going to be the magnitude of u. So I'm going to calculate the magnitude of u. Okay, since it's in component form, I can just square the x part and square the y part. Okay, so that's telling me that the length or the magnitude of u is actually 5. I want the magnitude of v to be 40, but I want it to go in the exact same direction. So what that tells me is I want v to be, what is this? This is 5, I want it to be 40. I want it to be 8 times as long as u. Okay, u, the magnitude of u is 5. I want v to be in the same direction, but I want it to go 8 times as long. So I'm going to do 8 times u. Okay, so that's negative 32, negative 24. Okay, I'm going to sketch this to show you what that looks like. Okay, so that was u. If I did negative 32, 0, 0, negative 32 to negative 30, negative 24, that's going to be somewhere out here, which means vector v is going the same direction, but it's actually 8 times as long, which is what I was going for. If you want to verify the magnitude, you could do this squared plus this squared and then square rooted. It should give you a result of 40. Okay, one more example. It's similar to example 3, but it's trickier because we're going to get smaller rather than bigger. Okay, so for the last example for today, it says find a unit vector u in the direction of 3, negative 5. Okay, and if you recall, unit vector means that I want the magnitude of u to be 1. Okay, you don't need to sketch a picture. I really am just sketching the picture so you can kind of visually see what's going on. Okay, so I'm going to graph 3, negative 5 is the component form. So somewhere down here, okay, that's the direction I want it to go in, but I only want it to be a length of 1, which means it's actually probably going to get shorter. Okay, so probably I want it to be only like here to here or something like that. Okay, I want it to go the same direction, but it's got to be shorter than what it currently is. Okay, so the first thing I'm going to do is I'm going to calculate the magnitude of the vector they gave me. So let's see, what's the magnitude of 3, negative 5? Should I give it a name? Let's call it w, just for the sake of notation. Okay, so that would be 9 plus 25. So the magnitude of w is 34, which means w is the big one. Okay, now the square root of 34 is bigger than 1. Okay, so I need my vector u to be smaller than my vector w. Okay, so let me try to find u. Okay, so if vector w is 3, negative 5, and it has a magnitude of the square root of 34, and I don't want it to be the square root of 34, I want it to go to 1, I need to actually divide it by the square root of 34. I'm going to shrink each component by square root 34. Okay, this is my unit vector. If it would simplify, I would simplify it by rationalizing by square root 34. Is it going to help me? Okay, so my u is probably 3 over root 34 comma negative 5 over root 34, so it's going the same direction, but in order to shrink its size, I had to divide by the square root of 34.